Ladies and gentlemen, I'm happy to welcome you to the webinar by Smart Wires in the context of CIGRE SEERC. But also we are a member of Current. Current is also co-hosting today's event that's about innovative mobile and temporary power grid solutions, evidence from a project in Austria. Next slide, please. So briefly to, I'm myself, Susanne Mies, I'm the General Manager Germany for Smart Wires and also the board chair of Current. Just to set a big context, what we need, of course, is intelligent solutions for net zero, an agenda that has become even more challenging now with the Ukraine war that was started by Russia, with security of supply concerns and skyrocketing electricity, oil, and gas prices. We have a simultaneous gas, oil, and electricity crisis as we have never seen it before. And when you look at the time horizons that are on the left side here, 2030, 2035, 2040, 2045, what we see today is an acceleration on all of those. My home country, Germany, has decided to go net zero by 2045. And we also see in the European Commission Repower EU an acceleration towards the targets that we want to reach by 2030. So there is an issue of rising electricity, of course, electrification, and the networks are of public interest and are essential here. Of course, grid optimization is a very important part of that story, and a story that yet needs to be fully understood. What are the incentives for such intelligent solutions, and what could be a broader system perspective? Next slide, please. So the question here, our webinar is talking about a project that we have done in Austria together with APG, and is talking about mobile and temporary devices. The first question to clarify is, how long is temporary? And the answer to this is clearly it is from 1 week to several years. For example, if an optimization technology comes in when the build-out network comes late, that is temporary. And I also want to stress here that Smart Wires, the members of Current, are not saying that more grids are not needed, but it's very important that we take all of this, optimization, reinforcement, and more grids. All this is about speed, time is of the essence, and therefore technologies like ours can help extremely fast. I'm now introducing our first speaker. I also would like to, of course, welcome all the participants in saying that dear participants, actively please participate in this event. It's your event. If you have questions, please ask them through the chat, and we will try to take up as much as possible in writing back to you, but also in asking the question to the speakers. I'm happy to have such a distinguished speaker panelists for today. I have Stefan Höglinger from APG, Marie Hayden from Smart Wires, Jörg Leonhardt from APG, Professor Renner Theograz, Hassan Kaouk from Smart Wires, Christoph Maurat, boss of Consentec Germany, and then of course also Franziska Flaxbart from the Öko Institute Friederike from DENA, and Jan Kostevs, the team leader on electricity networks in ASA. So let us start this webinar with a keynote speech by Stefan Höglinger. Stefan is the team leader, corporate development, strategy, and innovation in the Austrian Power Grid, APG. And he's going to share with us his view on the role of innovation for APG. Stefan, the floor.
Hello, everybody. Next slide, please. So I would like to start my presentation with one slide showing the big changes we face in the future, because we think in the future there will be a radical change in the energy system. And I would like to start with maybe the biggest drivers in this, which is the renewable energies sector. So in Austria, we have 2019, we had 1.4 PV installed, but now it should go up 8 times higher, up to 12 gigawatt. And also in wind, we have to triple the installed capacities. This is a huge impact on our system on the TSO level, but also the system will be decentralized. We have now we have small units in the field, PV and so on, and not the big generation power what we had before. We see also one big chance to digitalize our world, which could be a driver for new improvements. But another driver is the democratization. So now we have active consumers. We speak about this prosumers. We have energy communities in the future, and also e-mobility will be a driver. Another one is the decarbonization of the industry, of other sectors. For example, in Austria, we have an energy consumption, electrical energy consumption of 70 terawatt. And if only one company, the biggest company, the steel company first, will change all his energy consumption to electric, then we have 33 terawatt hours, so half of the electrical energy in our grid. Sector coupling is also one big issue, which I think could be a challenge, but also gains new things which could help us. And last not least, but there is the ongoing market integration on the European level, where we exchange balancing products on a shorter time scale, but also we have this, for example, 70% obligation that we have to bring 70% of our interconnections capacity to the market. So altogether, we think the future is electric, is for sure, and we need some new tools for this new challenges. And this is R&D. Next slide, please. And I would like to show you how we think we can develop this. We think out of our R&D strategy that there are 3 dimensions we have to cope with. First is new flexibilities, where the customers are in the focus. Second, we have to optimize the existing infrastructure, our grid. And third, we have to invest in new technologies to have the necessary hardware for this 100% integration of renewables in place when we need it. Coming to the first dimension, I would like to highlight some of the most important initiatives we have this year. So in the first dimension, we have this vertical market integration and industry for redispatch projects. We need a platform where also new smaller units like households, aggregators can participate in the future on the flexibility market to be integrated, and that we also can use their help for us and also for the distribution grid to integrate all these new flexibilities. The second one is the optimization of the existing infrastructure. There we have on the asset management, for example, research projects where we think about the climate change impact on our grid. So what is in 2050? Do we need new pylons? We think, or we believe that the avalanches will be having a huge impact on our side. And so we need to know this right now that we can invest in the future. There we have also the new sensors where we can use them, for example, in transformers, maybe overload the transformers a bit without damaging the health, and so reduce maybe some redispatch costs for the customers. In terms of sustainability, you maybe know that this F-gas regulation or law from the EC is out now, that SF6 is banned from the substation by 2030 or 2032. So we need to see and look at all these alternatives right now to come to this goal. We also are dealing with assistance systems, for example, with the drones. Beyond visual line of sight, drones fly over 100 kilometers over the line and inspect the line, maybe if there are faults, so we can bring the line to power again very fast without using too much redispatch costs. And last, in the sector of network development, we also think about a new way of having this sector coupling done by making a power to gas pilot project, but there we need a market test. And the last one is the new technology, and this is related to this webinar. There we see look at grid boosters, so two couple of batteries where we maybe can manage load flows better. We think about new carbon fiber conductors. They have really good advantages, but we have to have a closer look and invest in this innovation. And last not least, this pilot application with smart wires. We need to steer our loads in our grid in the right way. And this power electronic based phase shifting transformer alternatives, they have some advantages, and we have to look at it. And you just can learn if you try it out. So this is just a small glance of our projects. I think that what is really important is that we always have to think about the maximum added value, which we need for the electrical system in Austria, because we need a secure and affordable grid in the future when we want to face these new challenges. Thanks.
Thank you very much, Stefan, for this introductory statement. I'm now handing over to Marie Hayden. Marie Hayden is the Chief Engineer of Smart Wires. She had previous positions with Smart Wires as Vice President Business Development and then also General Manager Europe. She's joining us from the US, early start for her. Many thanks, Marie, to share with us your view on how Smart Wires mobile and redeployable solutions are going to develop further in the future.
Thanks very much, Susanna. I might move on to the next slide. So yes, good morning from a very sunny North Carolina here in the United States, and of course, good afternoon to everybody in Europe. I'm very happy to be participating in this event today. I think we have a lot of experts on the conference, on the call, and it's a really good opportunity to learn from each other, which I think is exactly what CIGRE has been promoting for more than 100 years. So it's a very good event to be having. As Susanna mentioned, I'm the Chief Engineer at Smart Wires, and I was previously the General Manager of Europe, where I was leading business development there. And in fact, I led the team who first approached APG with the idea of doing a trial project of our technology on their grid. So I'm really looking forward to listening to the presentation this afternoon. I would like to also just compliment the team at APG, because what they did, I think, was remarkable. They set about trying a new technology on their grid, and you'll see that the timescales in which they achieved that I thought were phenomenal. I've worked with transmission system operators for more than 30 years. I worked in Ireland for 25 years at EirGrid, and I know that when you put new technology onto your grid, you have to bring a lot of people along with you on the journey, the operations engineers, protection engineers, asset management, safety teams. So it takes a lot of careful collaboration and planning to deliver something like this, and I thought the team did an exceptional job there. So congratulations to everybody involved in this project. I just wanted to take a few minutes to tell you a small bit about Smart Wires and our product development and our history. I might just go on to the next and only slide after this. What you can see here is a set of pictures showing some of our technology and how it has evolved over the last 10 plus years. But as it turns out, the technology that SmartWires started out with, the Guardian technology, actually started its life as a research project at Georgia Tech University here in the United States. So the team at Georgia Tech, they were looking at the different challenges that were being faced by transmission and distribution system operators in the US and around the world, many of which were coming from the difficulties of building new power lines. And one of the things that they understood was that there can often be a lot of spare capacity on a grid. Unfortunately, it tends not to be where you actually need it. And so companies are trying to build new infrastructure to address capacity shortages on one part of the grid when there might be capacity surplus on another part of the grid. And so they set about developing power flow control technology that would allow the system operator to route power away from congested and overloaded lines onto the underutilized capacity. And this Guardian technology that they developed was based around the idea of a distributed series reactor. So why did they go for distributed? Well, they thought that the idea of having modular technology was quite a good idea because not only are the grid needs always growing and changing, but they can be hard to predict. And so when you set about putting in something like a series reactor on your grid, it's hard to know how big a reactor you need to put in. You might have a fair idea what you need over the next couple of years, but do you know what you need for 40 years? And the idea of the modular technology was that you kind of put in the number of modules that you require now or over the next few years, and then you can come back later and simply add more modules if the need grows and changes. And so that's how they set about developing the distributed series reactors and the modular technology. Around 2010, SmartWires Inc. was formed. It bought out this technology and took over the job of commercializing it. And over the last 10 years, working with about 300 engineers within the company, dozens of partnerships with experts in a range of areas like power electronics, thermodynamics, packaging, etc. And working very closely with a lot of our partner companies, we have evolved and grown that technology very rapidly. And around 2015-16, we identified, in fact, I think it was some of the German TSOs just turned around to us and said, look, these distributed series reactors are never going to really be meaningful on our grid. They just simply aren't moving enough power. So thank you, but no thank you. So we took that and we continued to work on the technology and made the decision to move over to static synchronous series compensation technology, SSC technology, which is capable of having a much greater impact on power flow control on a grid. It can both increase and decrease the impedance of the line. So it can allow you to either push power off an overloaded line or indeed pull power onto an underutilized line on a different part of your grid. In many cases, the solutions we work on and develop with our customers involve both an installation of a push on one part of the grid and a pull on a different part of the grid. And that gives you the kind of flexibility you need to manage constantly changing scenarios and developments on your grid. Of course, another benefit of series of SSC technology is that when it acts in series compensation mode, like a series capacitor, you can get a lot of additional benefits more than just power flow control. So the technology, it's kind of like a platform. It does power flow control, but it can also do things like power oscillation damping and provide a lot of stabilizing services onto the grid. So over the last number of years, we have been rolling out projects using SSC technology. Our very first project you can actually see in that picture on the left, where you can see just one device per phase, and each device is injecting 1 mVAR worth of power flow control. As you see in the middle picture, that technology was deployed in 2019, and the middle picture then shows a technology deployed last year in 2021, and that involves modules which can hold up to 5 mVAR per phase. In this case, you can sort of see that there are 2 modules connected together on each phase. So this is a 10 mVAR solution. And going over to the picture on the right, we're seeing a solution there which uses the next development of the technology, which was the 10 mVAR per phase modules. And again, here we see 2 per phase, so this is 20 per phase. And the idea of being able to add as many modules as you like remains consistent and throughout all of the technology evolution. Some of our solutions are 60, 70, or 80 mVars per phase. And in fact, we have solutions where we deploy the technology, and now we're going back and expanding the solution by adding additional modules on top of the ones that you can see in that picture. So that type of flexibility and capability to expand over time has proven to be very valuable by our customers. So I suppose we just kind of go back to, why we're here. I think Stefan said very well, the energy system faces a lot of radical changes. The drivers that change themselves are constantly changing, and we're seeing increasing levels of urgency about tackling some of the most serious problems. So we have an urgent need to address climate change. We also, in Europe, have an urgent need to address security of supply and a very changing grid there, given what's going on in Ukraine and in Russia. And of course, globally, we're seeing a very rapid rise in the cost of energy and associated energy poverty that goes with that. So there's an urgent need to get on top of those rising costs. And part of that, a lot of that comes back then to putting pressure, I suppose, on our customers to act quickly and to be able to manage some of these congestion issues. I suppose at SmartWires, we're really passionate about working with our customers to find solutions that address their needs. We develop modular products that can be manufactured, installed, and commissioned in less than a year from when they're ordered. And we're doing projects with our customers around the world that are designed to last anything from 4 weeks to 40 years using the same technology. So I'm going to hand you back now so we can learn more about one of those 4-week projects, and hopefully that'll lead to many 40-year projects with APG in the future. Thank you, Susanna.
Thanks a lot. And Marie, before I let you go, we have the first question, and I would like to bring this question to you. It's Pablo Narvaez. Hello, Pablo. Nice that you are here. So Pablo is asking you, Marie, so what is the life expectancy of the SSSC? Because, of course, this is very important when they are shifted. Does this impact the lifetime? Quick question to a great.
Yes, thank you, Pablo. Great question. Just a quick answer. So our products are designed for 40-year life, with obviously maintenance required during that 40-year life period. And moving the technology from one location to another doesn't impact that lifetime. As you can see, the technology is actually very transportable. It just fits in a standard shipping container and can be moved easily from grid. And we have already done that with some of the technology you can see on the right-hand side of this picture, where we did an installation and then we actually moved the installation quite quickly afterwards to address a more urgent need that came up. So we don't see any impact of moving the technology on the lifetime of the technology, and it is designed for 40 years.
Thanks a lot, Marie. And I'm now introducing Jörg Leonhardt. Jörg Leonhardt is an engineer first level from the asset department of APG. And Jörg was definitely our key partner here in realizing this project that happened last year in November. So Jörg is now giving us some evidence what happened exactly in this first deployment of the SmartWires MSSSC second generation in Gipsfeld in Austria. Thanks, Jörg.
Many thanks, Susanne. You can hear me and see my screen?
Yes.
Yes, perfect. So let me give some words at first about the motivation and the purpose why we did this pilot project in the grid of APG. Of course, we are facing very big challenges in nowadays grid operation, and we see the challenges which we will face in the future when we need to extend the grid. But we will not only need to extend the grid, we will need to utilize the existing grid up to its maximum in an optimal way and at a controllable risk. We have a huge experience in using PSTs in Austria since 2006. We have a good experience with them, but we also face that they have limitations. They are heavy to transport, they are not that flexible, and they are not that fast. And so we were happy that on the horizon there appeared a technology coming from the company SmartWires, which seemed to have benefits which are comparable with the PST technology, and we wanted to investigate this technical alternative. But we didn't just want to investigate it in theory. We think that a practical proof of concept would have a very added value for us to know about this technology more in detail, and also to identify potential remaining showstoppers which could block the implementing in the grid due to some technical reasons, which you can know the best when you install it as a demo project in your grid. So we wanted to gain the maximum experience with a minimized effort, and we wanted to gain this experience as soon as possible. And so we decided last year to go for a demo project. The procedure was the following. We decided to use the available mobile equipment from SmartWires, which was available at this moment. This was the second generation of the mobile smart valve. We have had a trilateral cooperation agreement with APG, SmartWires, and we took Technical University of Graz within the boat to perform some dynamic risk analysis for us. We needed to determine a proper place where to install the mobile unit into our grid, a substation where we have minimized risks and minimized effort. I show it on the slides later on. So we performed several risk assessment with Technical University of Graz according to dynamic risks, and also internally in APG how to minimize the operational risks with installing such a pilot, and minimizing also the effort and the internal resources. And we decided to go for a 4 weeks pilot project in autumn last year, and we didn't buy these devices. We had a lease contract with SmartWires. Here you see the project timeline. It's not the full true, of course. We are in contact with SmartWires since many years now, with many feedback loops, what to be improved in the technology, and how we can make a test. But finally, the contract and the cooperation agreement was signed in August, and the preparatory works for transportation and deployment and the local dynamic risk analysis took place in about 3 months until November, when we had the commissioning in last November, 18th of November 2021. We had it 4 weeks in operation, and we tested on 8 dedicated days where the load flow was appropriate and the risk was also less. In spring, we gathered all our measured data and were working on the reporting. And we are now also still working on the further analysis of the system needs and where there could be possible follow-up projects together with TU Graz. So here you see the chosen place to install the pilot. It is the outer feeder of one of our substations, and the substation had the possibility to install such a device on the border of the substations, and it was easy accessible with minimized risk and minimized resources. Here you see in the next slide already the gravel road which we prepared, because the trucks, the trailers on which the devices are delivered are relatively big and designed with a big turning radius. And here you also already see the installation, how it is performed, and the part of the bus bars in the feeders were already removed. The device itself was placed into a feeder of a line between operational bus bars and auxiliary bus bar, and this substation had the advantage that this was very easy accessible here. So now I would like to show you some videos. Can you see it? Just one comment. Can someone confirm that you can see the video?
Yes, we can see.
Yes, perfect. Okay. So here you see the video of the arriving of the 2 trailers. I stop it just to highlight. Here you see metal plates needed to be positioned in order to assess the substations because of the turning radius of the trucks, which were designed for American roads and not for European roads. So one of the challenges we had with this generation 2 maybe we will discuss it later on. The next generation will not have these challenges anymore because it, I think, will fit on a 20 feet container. So this is some kind of lessons learned we had. So very short video just to show you how we brought the trucks into the substation. I proceed with the presentation. Here you see the trailers already parked in front of the operational building of the substation. Here we made also our small control room from which we controlled the devices remotely with antennas via, and so it was not connected via fiber optics, it was connected via radio controlled in this generation. On the left side, you see the guest trailer, which carries the insulators and one pod with the devices. And on the right side, the truck is the so-called host trailer. It hosts the devices, and you see these metal frames here. On this metal frame, the whole devices will be mounted afterwards. I have a time-lapse video of it, which I would show you partly now due to time restrictions. I skipped to the second day. It took us 3 days to install it. And on the second day, it's getting morning in the substation. The crane is already there. And you see that the crane positions now the pods, the 3 phases from the guest trailer on the ground. They were pre-mounted on the ground, and then they were put to the host trailer, which carries the devices. And after all devices and 3 phases of the load flow controlling smart valves are fixed, the trailer is put back into the substations. The outriggers of the host trailer are stabilizing the whole thing. And I just show you this impressive time-lapse video of the second day. On the third day, we made the wiring. And on the 4th day, we started with the commissioning, doing step-up voltage tests and all the necessary things you do when you commission high voltage equipment. When it was commissioned, it looked like this. You see in the bottom of the frame, you see the 3 modules. We didn't go for 5 modules, which would fit in these frames. For us, it was enough to use the available 3 modules, 1-1800, which means the modules could carry 1800 ampere, which was by far sufficient for our test. And these are the 3 green marked modules. And the bypass is the module marked in red. And on top of it, you have a filter. With this device, we could switch power in an amount of 20 megawatt, which seems a little bit, I always say, homeopathic in the TSO grid, but it was enough for our proof of concept and our tests. Just a short sequence of the connecting. So we connected it directly in the line. You see here the line disconnector is closing. This was not the commissioning connection. It was just for doing this nice video. And then you connect it with an operational busbar, and the operational busbar was connected via the busbar coupler to the normal grid. So only this one line, this one feeder was controlled with this mobile device. We performed tests on 8 days in these 4 weeks, on days when there was a very good load flow condition to do the tests, and when we had also the availability of our people to do this, because we had to be in the substation. We didn't perform it remotely via the SCADA system, but in the substations. We tested the several control modes and the expected behavior. So there are control modes. One can inject a fixed reactance. You can inject a fixed voltage. You can control the current and set also set points to the current which you want to have on the line, or have a threshold and a hysteresis in which the current may vary. We tested all these control modes, and we also tested the fault behavior, that in case of a fault on the line, the system must be bypassed, and this was also tested successfully. We have made several measurements in these 4 weeks. The harmonics were tested by our subcontractor Artemis, and they were all within the limits. We measured also DC currents together with Professor Renner from Technical University of Graz in order to assess the amount of DC currents infed into our system, because that could cause problem in the noise of the transformers or resonance effects on measurement transformers. This was also measured, and we have had some interesting results also from these measurements. The system was in the end decommissioned on the 17th of December within 3 days. So that is very fast possible and very smooth. And so I can just give you the conclusions and the lessons learned. The key conclusions are that the system behavior was as specified and expected, of course. The cooperation was excellent between SmartWire's experts, APG, and the Technical University of Graz, and also the subcontractor that was in these times when there was a lot of Corona restrictions and containers was a big risk to ship it over the ocean. I think we were lucky and had a very good cooperation with them that we could make this small demo project. The DC current emissions would need to be monitored. This is an issue in power electronics, and we could measure that, and we are in close discussion with SmartWires how to minimize them, and this solution is also found. You need to do more detailed studies with the protection department. This depends very much on the mission profile you want to drive with such a load flow controlling device. It depends if you want to operate them in a preventive mode, which means you inject permanently and change the impedance of the line, or if you want to operate them in a curative mode, that means only in case of a failure in the grid. So this is decisive. So these are some lessons learned, what is impacting what you need to do if you want to include such a system in your system. So thank you so far.
Thanks a lot, Jörg, for this impressive presentation and the very nice videos. I have 2 questions. I think one has been addressed already by yourself from Francisca, who was asking what are the feedback loops and the problems that occur. I think that has been kind of answered. In the interest of time, the other question very briefly was asked about by Alexander Weiss. So what do you do now? You have done this pilot project. Are you going to go for additional SmartWire systems in similar stations because it's just a fast deployment, or is there any other studies that need to be done? So if you want to give a brief answer, we have also Professor Renner, who can certainly also provide some input on that, but maybe you're very quick and dirty on that.
Yes, quick and dirty answer. We have a lot of upcoming projects in the grid where we need to install load flow controlling devices. Also PST projects can be found in our National Grid Development Plan. And we can now make up our mind with the knowledge which we gained into this demo project, if we can go for a technology open tendering for such load flow controlling devices, what needs to be clarified APG internally before in terms of protection. What do we want to use them, preventive or curative? So we now have a lot of experience what the system is capable and how we would need to do the tendering documents, or how we need to assess them, and what if it's really comparable with a PST, and how to include such things maybe in the grid development plan of the future. Yeah.
Many thanks. So there's several other questions, but we are already a bit behind time now. That's why I would like to now introduce our next speaker, which is Professor Herwig Renner. Professor Renner is professor at the TU Graz, and he is working in the field of power quality and power systems dynamics. He's also a member of several technical committees in CIGRE and SEERC, and he's going to explain to us a bit the behind the devices, the studies that have been done simultaneously with the pilot project. Professor Renner, I hand over to you.
Well, thank you very much for the introduction. I will just give you a short idea about the studies we did. So the next slide, please. As Marie mentioned, these devices are capable of providing quite high dynamics, which is maybe not really necessary for power flow, but for other tasks. On the other hand, the grid operator had some concerns about that high dynamics. So would there be the danger of having some oscillations, some instability in the system? So they asked us to do some studies to at least get an idea about the possible risk. So could we go to the next slide? Just to give you an idea how the device is working. Basically, it consists of several modules, several stages, which are built like the one presented here. So it's basically a capacitor and 4 switches now connecting this capacitor to the grid. So in the diagram on the top, you see in blue the line current and the ideal injected voltage, the orange line, which is either lagging or leading by 90 degrees, depending on the control mode you're operating in. Well, in reality, it's not an ideal sinusoidal voltage, but if you have just a single stage, it would be something like this rectangular voltage, this dashed line. So the capacitor acts as a voltage source, which is connected in a, let's say, correct way. The next slide, please. So basically, you could reduce it to an ideal voltage source with a capacitor in series, and which in a synchronous way changes its polarity. So that led to some questions like, is there a risk of resonance? Because we have a capacitor now in series. Is there the risk that there could be some resonance and some oscillations? And the other question was, during the operation, could there be some interaction with power plants? So nearby the site where the demo was installed are several hydropower plants, and we try to investigate if there could be some controller interactions or some synchronous oscillations. So can we take the next slide, please? So basically, since we had in this demo 3 modules, it's basically 3 times the ideal voltage source plus the capacitor, and it's now from the top to bottom a cycle of having 1 capacitor, 2 capacitors, 3 capacitors, or then going back, then changing the polarity, going up again and down again. So it's a continuously changing configuration. So if you try to estimate a resonance frequency of that internal capacitor with a typical grid inductance, so we are assuming some minimum and maximum short circuit capacity, you will get a resonance frequency in the range of 10 to 20 hertz, which means a cycle length of, let's say, 50 to 100 milliseconds. And that is significantly above the length of each switching state, which will change every 1 to 3 milliseconds maybe. Which on the other hand means there should not be any, let's say, stable oscillation. So the question, is there could there be a resonance problem between the internal capacitors and the grid, can be answered, no, there's no risk of resonance. Next slide, please. So then in the next step, we set up a dynamic model of the grid plus the load flow controlling device. So the manufacturer provided a very good RMS model for Dix Island Power Factory. We had quite a good dynamic model of the system, including the hydropower plants, each generator equipped in a model with a governor and a voltage regulator. And we did some tests like investigating different power flows, setting events like short circuit, tripping of lines, changing of the operating point. And we did an analysis of the voltage and currents and the rotor angles of the machine. And if we go to the next slide, you see one example of those tests. You see, of course, there are some oscillations, but they do not differ from, let's say, normal operation without a load flow controlling device. They are well damped. We had no problem of some instability or anything else. So also that question could be answered like there should be no risk of instability with the operation of the device. And that was basically also confirmed with the device in real operation. So yes, that's maybe a very, very specific part of that project, but I think it's also necessary in advance to check those things. Well, that's all. Thank you very much. I hope I could catch up with the time.
Yes, many thanks, Professor Renner. We will have time for the discussion, I hope, later. I hand over to Hassan, who is going to briefly complete what was said by Jörg and Professor Renner on our side, Smart Wire side. Hassan Kaouga is a customer solutions engineer with Smart Wires based in Berlin as myself. So what's your perspective, Hassan, on this project from our side?
Thanks, Susanna. Thanks very much. We can move to the next slide. So before, I just wanted to give an overview, to go back a step and see what mobile solutions really represent, and the interest from APG coming to look into mobile solutions even more. Right? We mentioned in the beginning, avalanches happening, natural disasters, that things we do not account for, and you need a solution that basically can be quickly deployed, like Jörg mentioned, a couple of days, and also movable, basically on wheels. So mitigating for emergencies, congestion management, having a short-term bridge when there is a need for maintenance or when there's a need for projects that need to be operating a line, for example. So mobile solutions are something considered not only by us, but by different flexible solutions for the grid. If you go to the next slide, and Jörg and Professor Henna have already talked a lot about the project. There's nothing really much to add in terms of technical sense, but key takeaways that we have had. In terms of collaboration, it was excellent among the three parties. We definitely learned as a company about what challenges could come and how can we make even the whole process faster. Despite the devices not being ISO fit, the road permissions acquisition was not that hard. The future generation of these devices will be fit to fit the European and international standards, and permissions will be acquired instantly. There was minimum resources required from both sides. On our hand, from Smart Wires, it was a handful of people working on this. From APG, the colleagues can confirm. And that's what you want to look when you allocate assets that are movable. You need to also allocate resources that are movable. And when you have minimum resources required by the utilities, that's even a plus. And most important is the time frame of installation that was within days. Jörg maybe can even confirm. He mentioned several times when if we would do it again, it would even take less. So, and basically then actual installation time was in the matter of hours. So overall, it was an excellent project in total. And we definitely learned a lot from both sides, and definitely the illustrations from Professor Renner from TU Graz were very helpful for our insight on the technology. Thank you so much.
Thanks a lot, Hassan. And now we leave this very interesting pilot experience and go a bit to the big story back again. Christoph Maurer is Managing Director of Contentech, electrical engineer, well-known expert on transmission challenges. And he's going to talk us through what we could call moving hotspots. What's going to happen, especially in the German power network in a very near future. Christoph, the floor is yours.
Thank you, Susanne. Thanks for having me. Could you proceed to the next slide, please? So, welcome from my side. I just wanted to introduce you to, let's say, the challenges we will be facing regarding transmission infrastructure over the coming decades in Europe and in Germany in particular, where I come from. So if you look at the German energy transition, I think we now have lost almost a decade over the 2010s without achieving significant progress due to various reasons. But now we have a new government, and we are now rapidly ramping up our ambitions. At least, I'm not sure whether we'll, let's say, we'll be able to satisfy our ambitions, but ambitions are rapidly increasing. So we now confirmed, or the government confirmed, that they aim for having 80% renewables share in the electricity system until 2030. So just for the sake of comparison, currently we have about 45% renewables share in our electricity system, which is quite a lot for a system which, well, cannot rely on hydro generation, for example. And perhaps even more ambitiously, we now aim at having a carbon neutral electricity system in 2035, so which will mean 100% renewables-based generation. Obviously, some of that renewables-based generation will have to be dispatchable, meaning it will have to be based on hydrogen, which is produced from renewable electricity. And we aim at having achieving climate neutrality in our system until 2045, so covering all energy sectors and all further sources of greenhouse gas emissions. But that will mean that the electricity system will grow even after 2035. So we will have a limited electricity system in 2035, which shall be fully decarbonized. But later on, we will need additional electricity sources to decarbonize other sectors. So looking at the number, that will mean that largely until 2030, we'll have to achieve additional RES installations in the range of, let's say, more than 20 gigawatts per annum of solar capacities and roughly up to 10 gigawatts per annum of wind onshore capacities. Additionally, about 6 gigawatts per annum of offshore capacities, at least in the later part of the decade. Though these are very ambitious targets, and we do not really know how to make it. So technically that will be possible, but there are a lot of issues regarding acceptance and so on. But one issue which really concerns me is the availability of transmission infrastructure. So all that electricity production from RES, even if we have the devices themselves, will only be able to realize with significant amount of additional transmission capacity. Though you should be aware that even today we have a high level of congestion in the German transmission system. So our annual congestion costs amount to roughly 1 billion euros currently. So including a lot of curtailment of renewable electricity, but still today with a lot of dispatchable fossil-based generation, we have the options to deal with congestion and to adjust generation patterns flexibly to the needs of the transmission system, but that will no longer be an option in a carbon neutral system. So if we want to achieve carbon neutrality in 2035 for the electricity system, there will be no room for fossil-fired redispatching and remedial actions, congestion management. And if you look at the current network development plans, the diagram on the bottom of the slide shows the circuit kilometers in the German transmission system. On the left for the existing grid today, in the middle for, let's say, the current network development plan, which was recently adopted by the NRA Bundesnetzagentur, but which currently only aims at a RES share of roughly 75% for 2035, so much lower than the current ambitions, just recently increased ambitions. And on the right, you find a study from ourselves where we investigated what might be the demand for transmission line circuit kilometers in the German system for a climate neutral system in 2050 or 2045. So if we look at what we achieved in progress over the last years, I think and conclude for me that the lack of transmission infrastructure may really be one of the single most relevant barrier to achieving climate targets in our electricity system. So if you could proceed to the next slide, please. That makes it, well, highly important to think about solutions, and we at Constantec, we are quite convinced that mobile and innovative solutions can contribute here. So just recently we finished a study for Current, so association of innovative solution providers for the transmission system. And within that study, we showed that such innovative solutions like SSCs, like dynamic line rating, like superconducting cables can significantly contribute to reducing congestion in the European system, and by that facilitate the integration of renewables. And we also could show that all these technologies luckily behave rather complementarily. So it's not that one is a substitute for another smart technology, but they all can contribute. But what's also important to stress from our perspective is that these innovative technologies are quite effective, but they are no substitute for conventional grid expansion. So we will need conventional grid expansion as well as a broad range of mobile and innovative solutions in order to deal with the challenges we are facing. And just on the question of mobility, I brought a picture or two diagrams from reports which are on regular pattern published by the German NRA Bundesnetzagentur. So for every quarter of the year, they publish a report showing the intensity of congestion on the lines in the German transmission system. And now I just here printed two diagrams from a report from 2017 and another one from 2020. If you look at the diagrams, please note that they, in the meantime, changed the color code. So it's not that the 2020 system is less congested than the one in 2017, but rather that what was printed in light red in 2017 is now only, let's say, light yellow and looks less alarming. Nevertheless, it's the same amount of congestion here. But if you look at the patterns of congestion, you can really say that they changed within, let's say, quite a short time. So in 2017, the most pressing congestion was between the eastern and former eastern and western parts of the country. So in the southeast of the new states, connecting them to the region of Bavaria. So that was a line which was heavily congested for a lot of hours during that year, but network expansion took place there, and that congestion was relieved and is relieved now. And now we have other hotspots in the system, for example, more connected to offshore generation and transport of offshore electricity. So we can really observe that hotspots are changing in our system. And that's what makes mobile solutions, I think, particularly interesting. So we have a system which is heavily congested. We need a lot of innovative solutions, but we also are working on grid expansion. And that will mean that patterns of congestion will change over time. And having mobile solutions would allow to adapt flexibly to that changing hotspots. So to conclude, I think transmission expansion or satisfying the transmission demand will be one of the most important challenges to achieve our climate targets. And we need all available measures to cope with that demand for transmission. That includes conventional grid expansion, but it also includes mobile and innovative solutions. So thank you for your attention.
Thanks a lot, Christoph, for this very interesting overview and also funny aspect of changing the color codes. We are now going over, and we come certainly back to some questions related to your presentation, for example, east-west flows in Germany or stuff like that. Now we have a roundtable discussion with Franziska Flaxbart from the Öko Institute. She's a senior researcher there. We have also Friederike Wenderoth from Deutsche Energieagentur DENA. And we have Jan Koster from ACER, as well as Jörg, who has already shared his views. So the question to this panel is largely, are power electronics scary? I start with a kickoff by Franziska, who is going to take us through Franziska Flaxbart, the senior researcher, energy and climate from Öko Institute, going to share with us a bit the modeling potential of grid optimization perspective that he's seeing. Franziska, you can start.
Well, hello, thank you, Susanne. Well, I was asked if the future role of the network optimization, from my point of view, should take an important role in the planning of the future power grid, and I do very much agree to this aspect, and I also think that they should be integrated into the planning process at an early stage, for example, in the grid development plan. And now I'd like to explain why I think so. And me as an energy market modeler at the Öko-Institute, I do a lot of work on determining future grid expansion needs in high renewable energy scenarios. And I do it from a microeconomic perspective and not so much from a technical perspective. If economic beliefs are adhered to, there will be a need for grid expansion, as Christoph already showed in his presentation before, largely independent of the design of a future scenario, which will significantly exceed the need for grid expansion discussed so far. Consequently, the decision on how the grid expansion is realized is also of higher importance. There are good arguments from my point of view to solve the lack of transport capacity in the current power grid, not only by building new power lines, but also by optimizing the grid. First of all, there are the costs. From a microeconomic perspective, the use of power electronic solution would help to reduce the cost of grid expansion for society. Unfortunately, the economic calculation comes to contradictory results when evaluated from a business perspective by a grid operator in Germany. So this is a known incentive topic which has to be addressed. Secondly, there's the timing. I doubt that the required grid expansion can be achieved in the desired time when only using the classic solution. And this jeopardizes the achievement of climate protection targets. Because congestions in the power grid lead to redispatch, and redispatch currently means shutting down renewable power plants in favor of more CO2 intensive alternatives. And further, RES expansion can only take place in connection with grid expansion. In this respect, I believe that minimizing additional grid expansion requirements by including all technical alternatives is the order of the day. Grid optimization measures can usually be implemented more quickly than building up new power lines, so they are a time-saving alternative to conventional grid expansion. And my last argument is aimed at responsible use of the resources provided. There's already the NOVA principle in the grid development plan, which means network optimization before reinforcement, before expansion. And this principle, to my interpretation, ensures that resources have to be used sparingly. In times of high renewable energy sources, land use conflicts will become more important. If grid optimization measures reduce the need for additional power lines, they do also reduce land requirements. And there's not only land use as a resource, but also public acceptance. The transformation of the energy system requires all of us to accept certain changes and to be prepared to make restrictions. With this knowledge, on the other hand, the resource of social acceptance should be handled with appropriate care and respect. And this also means that as little new grid construction as possible should take place, but as much as necessary to ensure security of supply. So from my point of view, sticking to this rule and saving public acceptance could also help to speed up classic grid expansion projects, as published in a recent policy brief of the Öko-Institute. To conclude, also from this point of view, it should be said that grid optimization measures should be of particular importance in the grid planning process.
Thanks a lot, Franziska, for this answer provided. Friederike Wenderoth from Dena, you are going to tell us what are the regulatory obstacles, but also you're starting with the time horizons that we have, including now the recent G7 speed up. That's quite surprising also that G7 is speeding up all the ambition now. So you're going to react to this, and that's then also a perfect introduction to our last speaker here, which is Jan Kostevs, then after from ACER. You have the floor.
Thank you, Susanne. Yeah, G7. Actually, at the moment, I'm sitting on the European Energy Forum in Berlin, where the G7 energy ministers have had their conference last week, and the goal or the ambition they formulated, it's more an ambition than a final commitment, but it shows the direction where we're going, where they mentioned climate neutral energy sector by 2035. And I said, okay, let's go. But what does that mean for the aspect that we're discussing here today, temporal and mobile solutions? I mean, if we now plan to install a device in the grid in 25, and then the hotspot, as you illustrated, Mr. Mauer, is moving in 2030, and we can move it once again, and then we must have reached climate neutrality already. So this aspect is changing our roadmap and project planning timelines a little bit if we think about this. But this is not the only aspect that I want to mention here today, because most of us are planning still with a 80% renewables in 2030 in Germany and 2045 for climate neutral energy sector. We will see what the final commitment of the government will be then. I must say, I also really agree with you, Ms. Flaxbart, on the aspects of the grid development plan. And also what I thought was very interesting today to see is the video that you showed of the building site. I'm sorry, I forgot who showed the building. Was that Mr. Leonhardt? That was very interesting to see the asset moved from one side to the other. But my main argument I want to say is, you see in this video how easy it is to do the transport as a heavy transport in 2 days, but we have very extensive planning procedures and approval procedures for the asset in the substation itself. So we had the operational devices study here at the German Energy Agency, and also talked about this aspect with transmission system operators and also distribution system operators. And they all said the same. I have to do the planning process twice. What is the benefit of reusing an asset? I can move any asset that is not a specialty of a specific asset. I can move everything that is not built out of concrete, basically. And nevertheless, from a customer point of view, I must say, even if the economic advantage is small, we should consider and discuss it as we do today. And in single cases, it can be very interesting to do this. And therefore, I think it's great that we have this discussion here today. Nevertheless, let's also think about the grid planning department of the grid operators that must realize this in their planning processes and asset management. And think about it as a whole process chain of moving the asset, and not only that the transport can be made within 1 day. And here we maybe only not talk about how the asset can be moved from one grid operator to the next grid operator, where also the standardization of the surrounding devices in the substation must be considered, that they use the same tools in the end. Especially if there are different regions where building restrictions might be different. And at the other hand, I must also agree with the impact of the power electronics on the energy transition. And then we must still think about that the system and stability assessment of the placement of such a device must be also done again, and is crucial in any case, permanent or temporary. So if we talk about technologies like we saw today, I think that the system integration aspect is a more important aspect than if I move the device in the end. Nevertheless, it's worth to discuss moving it in specific cases. Yeah, I guess that's it from my side.
Thanks a lot, Friederike, for these insights. The Betriebsmittelstudie operational devices study that Dana has contributed to. Now we have Jan Kostets, So Jan is the team leader for electricity infrastructure of ACER, which is the Agency for the Cooperation of Energy Regulators, joining us today from Ljubljana, and we are going to meet tomorrow in the Infrastructure Forum in Copenhagen as well. So Jan, ACER has published a paper last year in November, and of course you are the ones overseeing what's going on in European infrastructure. What is your view on this? What is the future of power electronics? Heading over to you.
Thanks, Susanna. Well, first of all, it's very nice to listen to different TSO colleagues present pilot projects. Usually we're talking about pilot projects and the success of these projects. I think I heard many success stories across Europe, which just, I think, underline the fact that we have very capable engineers and very capable people at the TSOs doing very hard work. But we have an underlying problem, which is, in our opinion, and this opinion is now shared with the NRAs throughout Europe, which is blocking the path towards, say, going beyond just pilot projects, really implementing smart solutions wherever they would be beneficial. And I think this is quite a huge amount of opportunities there. And the blocking point is that we have to go back to the basics. We have to realize that a regulated entity, which the system operator is well, basically being regulated by a bunch of bureaucrats. I'm speaking very nicely here and very openly, who usually do not really have a clue on what, I see you're smiling, who usually do not really have a lot of technical clue, right, on what is the good solution for the TSO to do. What does that mean? I mean, it's nothing bad. Otherwise, it would be sort of a duplication of experts both on the regulated side and the regulator side. And it doesn't make too much sense. It means that if you do not have clue, then you leave the technical decisions to the system operator, and you just approve them where you believe that you trust the voice of the operator. But what do you approve? Actually, you approve the cost of those solutions. So basically, you say, okay, we will pay you through the tariffs, usually the costs of that solution, and usually you give a rate of return on top of that, so to cover any unknowns. And that's it, right? That was the typical, and still is the typical way the regulation works, not only in Europe but throughout the world. And it's totally fine if you're stuck with classical solutions, with building lines, building infrastructure the old-fashioned way, like it was done for the past, I don't know, 50 years or even more, 100 years more or less. Yeah, that's normal. But the problem is when you have smart solutions which are much cheaper and which may be sort of competitive to the classical solutions, that's where you face a problem, because the business side of the system operators does not see any sense in investing into smart solutions, smart, let's say, cheap solutions. So why would a system operator invest from the business perspective into a cheap solution compared to more expensive ones, which have been driving their business for decades and decades? And this is the problem we were trying to answer in our position paper that Susanna mentioned. And I believe we did find a couple of ways forward. One is that we should forget, when it comes to smart solutions, about remunerating costs, but we should look at the benefit side of the projects and share the benefits between the consumers who are paying at the end for such investments and the system operators who are running these investments. I believe this step is the most crucial one if we want a speedy move forward, right? This is something which would really transform the regulatory sphere, let's say, and would enable strong movements, we believe, from all system operators, both on the transmission and distribution side, towards, let's say, being more efficient. The other potential we see in KPIs, right? But KPIs, you know, these are sort of systemic overview of how the TSOs or DSOs are doing their job, looking at efficiency. Okay, so you set a group of very specific KPIs and you look at the activity of your operators. This is all good, but this is more a longer term solution. Maybe not a solution in itself, but a tool to monitor the effectiveness of system operators. And these are basically the main messages we are making in this very short position paper. The regulatory frameworks need to change. That is definite, because if they do not change, then we remain remunerating costs, which means that operators would always opt for more costly solutions, which usually are classical infrastructure solutions, which are getting harder and harder to build. Unless, of course, they're being pushed against the wall by the system itself that needs a fast, quick solutions, then they scramble to find something, you know, whatever it is, somewhere. Yeah. Thanks. That's my introduction.
Thanks a lot, Jan, for this statement. I think, of course, it's interesting to get the view of APG, Jörg, but also Stefan Höglinger, maybe responding back to you. I can only let's say agree from the Smart Wires experience in that sense that in National Grid UK, because of a very incentivizing framework, we have seen that we go far beyond a pilot. We are a mature technology. We have seen a 48 smart valve deployment there because the regulatory environment was beneficial. And we see similar things in some other countries, but unfortunately not sufficiently in Europe. So Jörg and maybe Stefan also, what do you think? What is needed to take APG now from a pilot approach to a larger deployment approach on such grid enhancing technologies? You were saying in the beginning, Jörg, that the PSTs have also some disadvantages. We talked about the need for redeployment and that kind of thing. So what is needed from a regulatory side to make you move?
May I start coming back to Jan's statement? I really thank you for this, because this is a problem we face from the TSO side since ages. So why should we invest in new technologies when it's much better remunerated to build new lines? We take the risk, and it's not always that a new solution, a new smart system is coming to the end with very positive gains. So we need a new regulatory framework which also incentivizes such risk-taking TSOs. And I have to say one comment to that there are not only investments or projects where the costs are maybe less if the solution is positive in the market now, because there are also investments in R&D which look on future problems. For example, we see that we have less inertia in the system in the next decades, so we have to look at the solutions right now. And this is not something where we gain or have less costs for the consumers, but we have to a better view on safety. So this is also taken.
Thanks a lot. Jörg, what are you thinking? What's the difference between APG and Tesla in adopting new technologies?
Maybe not between APG and Tesla. I would compare more the two companies, NASA and SpaceX, in the way they shoot the rockets to the space. While NASA is calculating for decades, building a new rocket and shooting one rocket in 10 years, a new rocket into space, the SpaceX does it the other way around. They deploy every month a rocket, and if it blows up, it blows up, and they have their lessons learned. this is unfortunately not an environment in which we live as a TSO. We have a system which we operate close to its limits already, and there's a big of more risks to come. And of course, the TSOs try to keep their high level of security of supply. And it is hard to say now I deploy a huge project with a new technology, increasing the utilization of my existing grid, maybe using such power electronics in a curative way. That means if a line trips, I can overload a parallel line by 150% because I have a power electronic device which reduces me then the flow to 100% very fast. This is something which is not in the soul of the TSO, that they like to do that. We will for sure come to such solutions. It will be needed anyway. But we need to be careful and go in stepwise approaches, and this is why such small pilots are needed in order to convince and prove the technical reliability. We see the biggest projects of smart wires in grids like USA, South America, and also Great Britain, where the TSOs is already used to such bigger uncertainties like island operation and things like that. I think in Central Europe we are a step away from that, and it's a little bit a chicken egg problem. If you never have a demo project anywhere, you will not come to deploy a very big project. So I think this was, for that perspective, this was a good step forward in Central Europe, and we see the projects now slowly growing. And I hope we will be fast enough to gain experience and to convince ourselves that these devices are reliable.
Thanks a lot, Jörg, for this. I would like to play this question also back to Christoph Maurer, but also to Marie. That means, are power electronics scary? What is the reason why the takeoff, in particular in continental Europe, is so slow? It's called slow and steady. According to ESO, that's the way to go. But in times of climate change, maybe ESO would have said faster, and steady is maybe better. So what's your perspective, Christoph? Is there a take-off of especially power electronics to be expected in Germany, or are we going to remain with the more traditional solutions? And Marie, maybe your broader perspective, having changed the role in several companies already.
First of all, I think one has to conclude that the takeoff has already started. So we are now applying power electronics for a wide variety of applications. For example, if you think about management of reactive power, which was in the past mainly done by analogous devices. So we're now relying on power electronics, and we need to rely on power electronics, though there's no alternative to STATCOMs, for example, to deal with the challenges for reactive power compensation in the German transmission system. There are some reasons, most of them were mentioned. So incentives for TSOs, financial incentives might not be optimal because mainly we grant a regulated rate of return on capital expenditure, not total expenditures. That definitely is an issue. But also what Jörg mentioned, applying a new technology. So TSO transmission business might not be the most innovative industry branch in let's say in energy systems, which is good and bad at the same time, perhaps. So TSOs somehow have the responsibility for system security and for the reliable operation of the system. So it's not a position to take risks really on the one hand, and innovation sometimes is a little bit risky, obviously. Therefore, it's necessary to, let's say, investigate and research in detail new solutions. On the other hand, well, having been working with TSOs for almost 20 years now, I can also confirm they are a little bit conservative, but the industry is changing definitely, and people who are working in the industry are much more open to innovative solutions now than they were, let's say, 10 or 15 years ago, the system we are operating today, I think some of let's say former managers of TSOs would have declared impossible to operate somehow. So I still remember discussions on what might be, let's say, the maximum threshold of renewable generation which could be integrated in our transmission systems, and they were much lower, these thresholds, which some TSO managers then announced than the levels we are operating today without any real concerns for system security. So it's challenging to operate this system, but it's not that it's insecure the way we operate it. So I think change is underway, and if you look at, for example, the example of grid boosters in Germany and all that idea of curative operation and acting in case of a failure, that was really, I think, a challenge for many of the TSOs, but they accepted this challenge and did a lot of research and now are adopting these technologies. Though I'm quite optimistic that we will see, let's say, an acceleration in deployment of such innovative devices.
Susanna, yeah, just to add to what Christoph said, I do think a couple of things. I don't think power electronics are scary, and I don't think transmission system operators see them like that. I think we see a lot of power electronics on grids going back 40 plus years, and obviously HVDC is a classic example. We see a massive expansion of HVDC across grids globally. So I don't think people are concerned about power electronics. I do think it takes quite a long time to embrace, learn a new technology and learn how it works on your grid and how it works and interacts with your existing grid and existing controllers. And for exactly what Christoph said, there's a level of conservatism there. A lot of it is necessary conservatism. You are dealing with critical infrastructure on national electricity systems, and it's not something where you can take significant risks. So I think that sort of conservative approach to going through the technical assure comes from the responsibility that grid operators have. And in the experience, my experience in smart wires and airgrid beforehand, I feel that typically what happens with technology like ours at smart wires is that when a customer does use it for the first time, that can take a while. And then the second one happens really quickly, and the third one, and then you get just this complete take up of the technology very, very rapidly. Definitely, we know that incentives and incentive regulation has a place in this, because we see it ourselves as a supplier of innovative technology globally. There's no question that the local regulatory setup is very directly correlated to where we see the fastest take up of our technology. So South America is a very good example of that, because there's a lot of competition in transmission. You don't really have competition in transmission as much in for example, Europe. And so those commercial forcing functions aren't necessarily there. So I think my takeaway is that they're not scary. I don't think people are scared of them. I just think it takes time for people to get their first project under the belt. I think when they do the first project, then the solution becomes part of the toolbox of solutions and starts to roll out across the grid. And that can be in mobile form for temporary issues like we talked about in this webinar, or for long-term solutions. So that's my take on it.
Thanks a lot, Marie. This takes us to the end of this very interesting webinar. This slide, just as a matter of conclusion, shows all these many reports that have been done, and it shows there is a lot of thinking underway from the Consentec study mentioned by Christoph on the complementarity of grid enhancing solutions. Wind Europe, the renewables industry claiming such solutions, ACES paper, as mentioned by Jan, studies done by the Watt Coalition in the US, or N3 Technopedia, that's an outstanding job in listing many technologies with pilots and projects. So embracing new technologies, changing a little bit some of the screws on the regulatory side, endorsing technology, starting with the Mount Everest of the first project, certainly the name of the game. I would like to thank all the speakers. This event has been recorded, can be seen once more, and wishing you a very nice end of the day. Bye-bye.
Thank you. Thanks, Susanna. Thanks, everybody.
Thank you.
Thank you,
Susanna.
Susanna.
Bye-bye.
Great discussion. Bye.